Okay, good morning, everyone. I'm Zhifeng Ding from Tianjin University. Welcome to our series of virtual academic seminars to celebrate the launch of SmartMed. SmartMed is an open access journal co-launched by Willy and Tianjin University. I'm one of academic editors of SmartMed. The editors-in-chief of SmartMed are Professor Wenping Hu from Tianjin University and Professor Hua Zhang from City University of Hong Kong. Today, Professor Cie Sham and Professor Zhifeng Ding from the University of Western Ontario will give the 11th seminar. Now, please let me briefly introduce the first speaker, Professor Cie Sham. Cie Sham is a distinguished university professor and a Tier 1 Canada Research Chair in Materials and Synchrotron Radiation from Western University in Canada. He earned his bachelor degree from the Chinese University of Hong Kong, and then his PhD studying Ecl Spectroscopy with Mike Bancroft at Western. He was on the staff of Brookhaven National Laboratory for a decade. In 1988, he returned to Western as an associate professor, promoted to professor in 1991. From 1999 to 2008, he was the director of the Canadian Synchrotron Radiation Facility at the Synchrotron Radiation Center, University of Wisconsin-Madison, building up capabilities and the Synchrotron community for Canada. He is a founding member and a beam team leader for 3 beam lines at the Canadian Line Source, a national facility of advanced photon technology in Saskatchewan. He was appointed in 2016 Officer of Order of Canada for his seminar contributions to materials and synchrotron science and service to the scientific community. Of more than 600 publications, which President Passion is 20,000 and the H index of 69. He has won many honors and awards, including the Helmholtz Prize, Top Prize for Research Excellence, and the Fellow of the Royal Society of Canada, J.C. Bryan Award of Canadian Society of Chemistry, and so on. He served as a member of the board of directors for the Canadian Light Source and the chair of the International X-ray Absorption Society. Today, Professor Sham will give a talk about synchrotron technology for discovering the science of scale in electronic structure of materials and dynamics. Let's welcome Professor Sham, please. Thank you.
Thank you. So now I'm going to share screen and show you what I'm going to talk about. Let's see. Okay. Good morning, everyone in Asia, and good evening, everyone in the other part of the world. Today, I'm really pleased to.
Sorry, I cannot see the screen. Sorry.
Oh, you cannot see the screen? Okay, let me try again.
Yeah, you don't share. Yeah.
Sure. Can you see it now?
No, not full screen now.
Okay, I have different screen. This one? No. Can you see this one?
I can see. Yeah, just two show slides. Yeah.
You can see, right?
Yeah, can see.
Can you see it now?
Now, okay. Thank you. Yeah, please.
Okay, sorry about the hiccup. So let's start over again. Now today, let me just turn the organizer for this opportunity to share with you some of the technologies that we've been working on for decades. So today, I'm going to tell you a little bit about synchrotron technology and how it can be used for material analysis. In addition to my role at Western, I'm also associated with the Suzhou Western Center for Synchrotron Radiation in Suzhou University in China. Okay, so what I'm going to talk about, the first thing I want to talk about is what is synchrotron radiation and why it is useful for materials research. And then I would make a connection to nanomaterials with desired functionalities. And then I'll bring the two things together. So what is the interplay between synchrotron teleology and nanoteleology? So I'll give you some examples to illustrate what can be done. And finally, I would give you some prospects, what is to come in the future. Now, what is synchrotron radiation when electrons are circulating at very high speed in a ring, then tangent to its orbit, it emits a very bright light called synchrotron radiation, as is illustrated here. So here's the electron, and here's the light it emits. Now, the light emits is tangent to the orbit, is in a very narrow cone, and in fact, it can be described by something called the opening angle. At the Canadian light source example, the opening angle is only 100th of a degree. That means all the light are coming out are highly collimated. So this is a good sign for microscopy. So now let's see what happens if we turn on. Let's consider synchrotron as a light bulb. When we turn on it, it produces a light with this spatial distribution. And within this spatial distribution, we have, say here, the x-axis is the energy, y-axis is the photon flux. We have infrared, we have UV, and we have X-rays. And the amount of X-ray, the energy of X-ray, really depends on the energy of the electron. In general, the higher the electron, the more X-ray you're going to get, and the brighter the light. So what does a synchrotron look like? So this is the Canadian light source before it was closed up. And so here in the middle is what is known as storage ring, where the electrons are circulating around the ring at speed close to the speed of the light. And then tangent to the orbit, there are ports where you can extract this highly collimated synchrotron beam which comes out. And then you build instrumentation called beam lines to do experiment, right? Be it X-ray absorption, be it scattering, and so on. Now the synchrotron actually is very big. It typically has the size of a football field. Okay, so what are the properties of synchrotron radiation? Why is it so useful? As I just mentioned, the most important thing is tunability. So when you turn on this light bulb, you have infrared all the way to X-rays, right? So if you compare this with the electromagnetic radiation spectrum, synchrotron actually covers many orders of magnitude of the length scale, right? And that is really, and the next thing is that it's very bright, right? It's very bright because all the light are confined in this very narrow forward direction, right? And if within this spatial distribution of light, you have all the wavelengths. You can tune it from infrared all the way to gamma rays. And then it also is polarized. So in the light beam that comes out, right, in the plane of the orbit, it is 100% linear polarized. So we can take advantage of that to do all kinds of experiments. And it is opposed as a time structure. In fact, the way the electrons are circulating are in bunches. And then between bunches, then you have a time gap. So therefore, you can use the time gap to look at decay experiments, to do dynamics, and so on, okay? And then a coherence, if you force the electron to wiggle in a device called undulators, then you can get actually coherent X-ray comes out, and you can use it for experiments, okay? And so, to summarize, if you ask what synchrotron is, it's just a tunable pulse X-ray source, basically, okay? So in the rest of my talk, I'll try to use examples to illustrate all these properties. Okay, so how do we track the behavior of material with synchrotron radiation, right? And that's the key. Now, the tracking can be done by scattering. So let's start from an atom. The X-ray comes in, it can be scattered. That means it changes direction. It does not lose energy. But if the scattering is done coherently by an array of atoms in a crystal, for example, if the wavelength matches the Bragg diffraction condition, then you can actually get diffraction, right? This is where X-ray crystallography comes in, and from where you can determine the crystal parameter using diffraction. Now, there's another scattering, it's called Neolotic Scattering. The X-ray tracking can part with part of this energy to do many fundamental excitations. For example, it comes in, gives part of the energy, so the wavelength gets longer, obviously. And this is an array of all kind of possible experiments from very small energy loss in the form of photon energy excitation to very large energy loss to compton scattering. So each and every of this energy loss is a good way for us to characterize materials. But today, what I'm concentrated on is not scattering, but absorption. Absorption really is the most powerful tool for materials analysis. So what do I mean by absorption? So let's start with an atom. So impinging X-ray comes in, right? If the energy of the X-ray has sufficient energy to excite a core electron, and then the X-ray is gone, the atom absorbs it. So this absorption normally is used to do a quantum transition from, say, the core electron to purely unoccupied states. In case of atom, of course, you have Ripple transitions. If you continue to increase this energy, and ultimately, at some point, you're going to kick the electron all the way into the continuum, right? So at that point, the electron will propagate away as a wave, spherical waves, and it disappear in a thin air. So if you measure this process in the form of absorption, this is what you will see. Before the threshold, and you see these so-called Ripple transitions, which are bound-to-bound transitions, right, approaching to the continuum, which is the vacuum level. And then above the absorption, what you see is absorption coefficient, which varies monotonically as a function of energy. Okay, so that's for a free atom. Now, what is important is when it's no longer free atom, when the atom is in a chemical environment, as in a bimetallic state, okay? Then, when the photoelectron comes out, gets excited, it doesn't disappear in thin air. It sees the atom is surrounding. And it brings back the information about the surrounding atom by backscattering. So you get backscatter, and the interference of that produce a modulation in the absorption coefficient, right? So this modulation is, right, in a molecule, the Ripple are quenched, you have a lumo appears, and you have oscillations above the threshold. Okay, so this oscillation is what is important because it contains all the information about the chemical environment of the absorbing atom. Okay, and this modulation is known as the X-ray absorption fine structures. And that is really the most important information or techniques we use in material analysis. I hope I can convince later on why this is the case. Okay, so now we talk about X-ray absorption spectroscopy. What is it? It's a measurement and interpretation of an X-ray absorption spectrum, right? So typically, when you look at so-called XAS spectrum, and you look at two regions, there's a region called near edge, is about 50 eV above the threshold. And then in the literature, you see things called SANES or LIXAP, they essentially the same thing. They also deal with the fine structure in the near edge region. Now remember, the fine structure contains all the information about the labeling atom, all the chemical information. Now, and there are also extended region, right, which goes as high as 1,000 eV above the threshold. Okay, this is called the extended X-ray absorption fine structure or XAPS. Right. Now, why is it divided in two parts? It basically have to do with how electron gets scattered when the kinetic energy varies. Okay, low kinetic energy undergoes multiple scattering. High kinetic energy electron undergoes single scattering. So this they can be treated differently because the theory is a little bit different. But anyway, the bottom line is XAS is a spectroscopy of absorption edges and fine structures. It doesn't matter what X-ray absorption spectrum you look at. It's always about the absorption edge, which tells you what element it is, what edge it is, and the fine structures, which tell you about what the chemical environment is. So therefore, it's an element and site or chemical sensitive technique. This is why it's so powerful for materials. Okay. Now, maybe just define one more time absorption edge. Absorption edge is just the threshold for the excitation of a core electron into the continuum, right? When you have sufficient energy to do that, the absorption coefficient jumps up abruptly, and that's the edge. So just give you an example what that is. Let's take as a molecule that most people are familiar with, right? The TMS. So we look at the so-called the KH, so exciting the 1s electron, and then you can see the absorption spectrum, which is so-called the SANS, the H region, right, right here, and which of course is these are bound-to-bound transitions to an occupied state. And as you go up in high energy, you have what is known as the XF. You see these oxidations, right? If it's a free atom, there's no oxidations. There's only a monotonic. So it's the difference between the monotonic and the oxidation that is the fine structure. And again, the fine structure contains all the information you want to know about the system. Okay, so let me just switch gear now a little bit, talk about materials, right? Materials really is the key of this seminar. I want to emphasize on materials of nanoscale, right? And I will take a couple examples that are the nanocomposites or heterostructures, because these are very peculiar, very interesting systems, and they are very relevant to the application of materials. So here's some of the materials we have looked at, right? Nitrogen doped carbon nanotube and so on. Now, some of these materials have some functionality. Say, for example, these guys and the tin carbon core shell, they can be used for batteries and so on. And these materials, they light emitters, zinc oxide, zinc sulfide, cadmium selenide, and silicon, and so on, optical devices. And bimetallic nickel platinum, they can be used as catalysts. And titanium nanotube, water spreading, among other things. And we also work on some ceramic nanostructures as a drug delivery drug carrier. So the functionality immense, and there's all kinds of possibilities. So the bottom line is, if you can control the morphology and the crystallinity of the nanostructure, then you can control the functionality. And the synchrotron is going to help us to understand this. So what kind of information can we obtain from X-ray absorption spectrum, right? So first of all, of course, we can obtain oxidation states, right? And we can also obtain some information about the unoccupied electronic states above the Fermi level, or the LUMO, and so on, or in the conduction band, depends on the material you're talking about. Okay, so let me just give you an example. And here are the two absorption spectrum of silicon, one in the chemical environment of a pure silicon, and the other is in silicon oxide, right? Obviously, there's huge difference in oxidation states. So let's look at the silicon. So what happens if the threshold energy is arrived, then the 1s electron gets excited and propagates away, and it sees the labeling atom and brings all those information back, and the result of that, it gives you the absorption spectrum of silicon. Similarly, when you excite the 1s electron, the silicon oxide, so the photoelectron goes out and sees the labeling atom of silicon in the first cell, and then of oxygen in the first cell, and then silicon in the second cell. It brings back all those information, and then it produces the end result is that it produces this absorption spectrum. Okay, so in principle, all the absorption spectrum contains all the information about the labeling atom. Okay, so one of the obvious parameter, of course, is the shift of the threshold, right? I mean, it's very obvious that silicon 4 is at high energy because it requires more energy to pull the electron out, right? Because some of the valence electrons are gone, so they don't get any screening. So this is the chemical shift. This is information you can get. Now, another thing is, see, you have a pit right at the absorption edge, right? And that's normally known as the white line. Now, this pit, say in the case silicon comes about from excitation of the 1s electron into an occupied p states in the connection band. Okay? So we're actually mapping the density of states. So this is what you see. Okay, and now the selection rule is dipole. Right? The selection is dipole, so S go into the p states and so on. And in the case of silicon dioxide, obviously, the band gap is different, the density of state is different, but you still are doing S to P transition. So if you look at the area under the curve, right, and which essentially is proportional to the number of 3p holes or the unoccupied states of 3D character. So by doing these two things alone, you already know a lot about the oxidation state change and electron redistribution in different compounds. So the next thing you can learn, obviously, is the local symmetry. So let me take titanium iron, in this case, in 3 different environments. Say in strontium titanate is in octahedral crystal field, right? And then in titanium oxide anatase and titanium oxide rutile, they are distorted, but they are distorted differently. As the result of that, the spectrum looks characteristically different, okay? So if you look at the so-called L32H, we're exciting the 2p electron into the D states in the case of titanium, right? So here you have this 3p half to EG transition. So let's just focus on the transition to the EG orbital, right? Obviously, because the octahedral crystal field, there's a degeneracy, you see a 1p. But if it's distorted, then you see 2 pits, okay? So when you look at the spectrum, you clearly see the splitting, right? And not only that, they have different intensity depending on the direction of the splitting. In fact, this kind of splitting can be used to identify the phase of titanium dioxide. So it's a very powerful tool. Straightforward, you don't even have to do any interpretation, and you know right away if you see something like this, you have a TiO2 in the rutile anatase state. Okay. So another information you can get, of course, is hybridization, right? By looking at graphite and diamond. And one of the approaches to use the density of states, another approach is some local chemistry. So let's start from graphite, right? Starting from graphite, we can think of benzene has a pi star and a sigma star transitions. But now graphite is a two-dimensional material. We can actually do polarization, take advantage of the polarization of the synchrotron, right? So in here is a series of absorption experiment with different angle, right? So what is this angle? So this angle, in fact, is the angle between the polarization and the molecular axis of the orbital. So let me just give you an example. In the case if it's a normal instance of the synchrotron with polarization lying this way, and that is the axis of the molecular orbital, then it's 90 degrees. And obviously 90 degree cosine 90 equal to 0. So when the angle is 90 degrees, we don't see any pi star transition, right? So if you increase the angle to more grazing, like 30 degrees, and obviously cosine now is approaching 1, which is 0 degree, and the intensity increases as you increase the angle. So the polarization of synchrotron is particularly relevant for studying of 2D materials, because with 2D, it's easier for you to orient the molecular axis with respect to the polarization. Now, in case of diamond, you don't have pi star, it's FPP saturated. Then you can compare the density of states. It's very clear. You can see, compared with the density state calculation, you clearly see this feature that's very unique to diamond. So you know you have a diamond. And diamond normally do not have pi star, but if you have some impurities, you can see a little bit. So by doing the absorption spectrum, it can allow you to test the purity of the diamond, right? And this is what you can do. Okay, so those are the three most common applications of X-ray absorption spectroscopy. So now I'm talking about some relating techniques, which are the excitation spectroscopy, right? One is called the X-ray optical luminescence, the other X-ray emission. Now there are a lot of materials, particular nano oxide structures, metal oxide structures. They can convert X-ray into visible. And of course, X-ray emission is X-ray fluorescence. And then the next technique I also talk about is a STIXM, is a scanning X-ray transmission microscopy. So let me now explain what X-ray absorption, X-ray optical luminescence, X-ray emission is all about, right? So let's say you have a semiconductor, you excite it, above the core, you get your absorption spectrum, right? And then the system is in excited state with a core hole, then the electrons can fill it. And the excitation process can be OJ and X-ray fluorescence. And these two processes can undergo secondary processes, and the end result of that, of course, is to give you electrons at the bottom of the conduction band, holes, and top valence band, and they can be combined to give you optical photons. If you use optical monochromator, then you can track it, and then you can see the bandgap emission, and you can see the defect emission, right? Okay, with a tunable X-ray, it can be site-specific, and because you get excited atom preferentially. Now, if you use a soft X-ray monochromator, and if the core is just below the valence band, or it doesn't have to be, but if it is, then you can also track the valence band. So you're getting your valence band spectrum by doing X-ray fluorescence. All right, so now we'll just use to use some example to illustrate some of this property of synchrotron and what you can do and so on. Okay. Now here, if I put a phosphor in here, excited with X-ray, then I get a visible photon now, right? And the mechanism is somewhat complex, right? And the reason this comes out is mainly due to thermalization of photoelectron, OJ electron produced, right? And then they can be combined with exciton formation, or they can come out as defects, right? So, but this information gives us a lot of information about nanostructures, okay? So in nanostructure, it's very important because zero arises from energy loss of the energetic electrons or thermalization. Now, thermalization has a path. So for electron to totally thermalize, right? So if it's in a big solid, it can do that. But in a nanostructure, the thermalization is truncated. So how do you understand thermalization? It's exactly the same way as people understand XPS, okay? So if I have a nanoparticle of this size, but my thermal thermalization path is a lot longer than that. So that means the electron will not be completely thermalized. That means the energy transfer to the optical channel is truncated, okay? And as a result of that, you have nanocrystal of different size. Their response to converting X-ray into visible light is different, okay? And this is the most interesting part about nanostructure and zero. Let me give you an example. We can do experiments in such a way we can have both the zero, in this case is a mixed phase TiO2 nanotube, right? And this spectrum is the zero, and this the vertical spectrum of the absorption. In fact, we can track the optical response as it scans across the edge, right? And in this particular titanium oxide nanotube, and we are asking the following question, because we started with anatase, and by and nearing it, it becomes a rutile. But we truncate the annealing process, so what we get is a mixed phase. So then the question, in a mixed phase, where's the rutile? Where's the anatase? And how is the phase transition take place? And we can get information by analyzing this in great detail, right? And you can see there's a drastic change in the branching ratio, which is due to a combination of where you're exciting and the penetrating depth of the soft X-ray. So I'm not going to go in that in detail. So the outcome of by analyzing the data, we come to the conclusion that the anatase to rutile phase transition is inside out. It starts from inside and then and out. Okay, the example is about time event. I said the synchrotron is a pulse. So how can we take advantage of the synchrotron or pulse, right? We can use it to many ways. One way of doing it is to see how the X-ray energy transfers to optical channel, whether it's fast or slow, how fast, how slow. So we can use some very standard gating experiments. Now, synchrotron is a pulse. At the advanced photon source, for example, right, and there's 153 nanosecond dark gap, right? Okay, so let's say if you look at a light-emitting material, when a synchrotron pulse comes in, it starts to emit, and then this is a dark gap. It decays until the second pulse comes in, right? So within this dark window, we can pick a fast window or a slow window, and by doing that, all right, we can see what the emission is, what the emission spectrums. So, for example, I say, okay, this is the emission or the luminescence spectrum within the first 5 nanoseconds, and so on, right? Okay, and of course, we can also single out a particular channel and get its decay curve. Okay, and we can also use both the energy snack and time-gated to do the optical X-ray absorption spectrum. Okay, this is the real spectrum based on the time gating and selected wavelength. I'll give you another example, right? So, for example, we look at two zinc oxide nanostructures. One is a nanowire, which is nearly a perfect crystal. One is a nanowire that has some defects. And then we do the same thing. We just select two windows, right? Say the fast window, we say from 0 to 20 nanosecond. So we look at, now this is ungated. This is the low time gating. So we can see crystal, in the crystal, obviously, the dominant is the band gap emission. And in the nanocrystal, previously we don't see a lot of that. But if you concentrate on the very fast window, we see a lot more of the band gap emission. So similarly, if you do the very the slow window, previously we don't see much of defect, and all of a sudden the slow window we see it's just mostly defect, right? So this time gating allow us to really understand the details of energy transfer into optical channels. So the next experiment is what is known as X-ray emission, which is a fancy word for X-ray fluorescence, right? Okay, so and as I mentioned earlier, this is how you get X-ray emission. I just want to give you an example of a very popular compound, the LQ3 for OLED, right? Okay, so on the right-hand side, we're doing absorption spectrum. So we're getting the LUMO pass and so on, right? And then the XES give us that's the occupied density of state. But it's different from the occupied density of state from XPS because this is the nitrogen component and this is the carbon component. And by looking at this, it's very clear the HOMO has only mostly carbon, it's very little nitrogen. And then by measuring the separation, and we can get the LUMO-HOMO gap. So it's a very powerful tool when you combine both of them. Okay, now the X-ray emission can also be done in two ways, because what I just tell you about is a transition from the valence to the core, as in the case of carbon. But if you have bigger atoms, then of course you also have other core levels, right? So those core levels can use it to fill the core hole. As a result of that, let me just take phosphorus as an example, right? Phosphorus, it fits this situation because in the 1s core hole at some 2p above before the valence band, right? So the core hole can be filled by this shell as well as the valence, okay? So if a cell is filled by the core, so it's metamic, then between two different compounds, say phosphorus of 0 and phosphates of 5 oxidation state, all you see is a similar feature, but you have a chemical shift due to the difference in oxidation state. But if you do the valence to con transition, right, then we get so-called the K beta in this case. And we can see very different spectrum. The reason being the valence band of black phosphorus is very different because it's a band where the phosphate is more narrow band, right? So this is a very powerful technique to understand the chemical shift as well the charge distribution. And fluorescence, of course, is also a dipole transition, right? So okay, all right, and this energy actually now is better than 1 electron volt with a monochromator, so we can do a lot of chemical analysis this way. Okay, so the last but not least item I want to talk about is scanning transmission X-ray microscopy. Okay, now this technique takes advantage of the coherence of the undulator, and we can focus it with a zoom plate onto a very tiny spot, right? In the SM beamline CLS, they can typically go to 30 nanometer, but it can go smaller. Okay, so basically, just like any other spectroscopy, you're moving the sample across the beam, right? So pixel by pixel. Okay, so let me just show you some of the results that we look at. We look at the zinc sulfide and zinc oxide heterostructure, right? So like that. So by doing that, so you pick this region, we can do microspectroscopy or spectral microscopy along this junction, right? So let's say going from here, we can look at the zinc LH excitation, and we can also look at the sulfur excitation, and we can also look at the oxygen excitation, right? So obviously, when we are onto zinc oxide, we only have oxygen. And when we are onto zinc sulfide, we only have zinc as a sulfide, right? Of course, you have zinc in both cases. So the interesting thing is that, and you can see that each of this slab give us a spectrum. So each spectrum corresponds to what we call the region of interest is in this step. So this is about 200 to 300 nanometers. So we can do nanospectroscopy on the region using technique. Okay. So making a long story short, we're doing all the spectroscopy, and we come up with the conclusion. And you can see once we go into the oxygen region now, the oxygen absorption pops up, right? Okay. So our conclusion is that in this particular construction, the zinc oxide actually are embedded into zinc sulfide. All right, I think I'm doing well in time. So now I hope I've given you enough example about how powerful synchrotron is and can be used for material analysis. So now let's talk about energy materials, devices, and so on. In order to understand those things, of course, the best study is in situ parental studies, right? So we want to track the chemical change as the device is operating, right? And we can do it both with X-ray absorption and X-ray emission. Okay, let me just give you a couple examples. Now, obviously, the hottest material in lithium-ion batteries is the lithium iron phosphate, right? Where the lithium goes in and out like this, okay? And of course, so we can use a simple modified console to do this kind of experiment. So the idea is that we look at the system during charge and discharge. Okay, so during charging, for example, right, and you can do a series of scans, and you can see the E0 is moving as we go charging from ion 2 to ion 3. And this is just another way of displaying where you can clearly see how the E0 shifts as you do charging. Okay, and similarly, you can also do the discharging, right? Here in the discharging, and you can, of course, you can see you're going back from IMD to ion 2 as you discharge. Okay, now this kind of experiment is unique for every type of material. Okay, so in this particular experiment, you use submicron lithium phosphate nanoparticles. If you change the size of the particle, that the behavior changes too. So this is sometimes why everybody doing same experiment, but they have different results because their microstructure is different. Okay, now, and you can see the direction is reversible. And we can also see the phosphorus, right? The phosphorus, we not only can see the ion, how it changes, we can see phosphorus changes. Of course, there's no chemical change of phosphorus. But when lithium ion goes in and out, it distorts the tetrahedral, sorry, it distorts the tetrahedral structure, becomes normal. Okay, so if you look at the phosphorus KH spectrum, you have this beam peak and you have this peak. Now let me talk about this peak. This is peak C, which is from the electrolyte, which is phosphorus hexafluoride. It doesn't change soon because of the electrolyte itself. But the phosphorus A and B are actually features from the electrolyte, and you can see this resonance changes. Okay, as lithium goes in and out, right? Charging, discharging, and you can really see it. The maximum changes, and according to the theory, this maximum has to do with the distortion, right? So that bonding changes. Okay, normally, if the maximum shifts away from the threshold, that means it gets shorter. If it shifts close to the threshold, it gets longer. Okay, so this example actually gives you an illustration of how X-ray absorption can be used to track chemical and dynamic changes in lithium-ion battery during the run. Now, the next thing I want to do is something we recently implemented. Is the X-ray emission spectrometer, soft X-rays, okay? And the unique feature is that we incorporate a glove box, so that means you can do air-sensitive materials. So this is particularly relevant for lithium-ion, sodium-ion battery operations and so on. So here I want to give credit to the three gentlemen who the beam-line staff, and they help build this instrument. And this is a custom-built instrument. We are working with a company called Ecal. And the technical component, the instrumentation, it just came out of this beam-line. But here I'm going to show you the science. Now we do a very quick test of the in situ experiment by using a composite of black phosphorus, graphene, and carbon nanotube in a lithium-ion battery, right? So here the absorption in the phosphorus KH, and you can see the phosphorus 0, which is black phosphorus, and you see some intermediate states, and so you see a very strong peak due to the electrolyte. Okay. Now, so when we do the emission, this is where the synchrotron comes in. We can, if you tune the excitation to below this high oxidation phosphorus, we excite only here. Then the only thing we are exciting is just the phosphorus 0. So because we are interested in how black phosphorus changes during the cycling. So here is just a curve that describes how the cycling is done. So by exciting this energy, we don't have to worry about fluorescence comes out from the electrolyte in the intermediate states because we don't have enough energy to excite them. Okay? So here are the spectrum, how it changes. We C here stands for charging, D stands for discharging, and the pristine, of course, there's no charge. And you can clearly see the cycling is taking place. Now, this is a very quick experiment just to demonstrate the capability, okay? So, and this is the K beta. So as I mentioned earlier, K alpha give you the chemical shift, and K beta give you the Venus band, right? Okay, and the science is still being written up, and we have a lot more detail about these things. So I think this comes to the end of my talk. I hope I give you some idea about what synchrotron is and what it can do. I'm personally happy to answer your question about how can you use synchrotron for your work. So at this point, I want to thank many people over the years, students, postdocs, research associates, visiting scientists, collaborators, and especially the synchrotron staff for all this work. And of course, all the organizations that I've listed here have provided all the support for the work. So finally, I also want to give credit to my group, my present group, including postdocs, research associates, and many undergrad students. And it was because of them I've been able to do all this. So at this point, I'm going to end. Thank you very much.
Hi, hi, Professor Sham, and thanks for your wonderful talk. Now I will host the Q&A session, and our staff have collected some questions from the live platforms for you to answer. I will ask the question on behalf of the audience. Thank you. The first question is for XTXM test, just you mentioned in the slides. For example, zinc sulfide and zinc oxide, can we in situ clear or heat the sample and monitor the evolution of the interfacial structure at the atomic level?
Okay, if I understand correctly, and you asked about whether or not it's possible to do in situ, right?
Yeah.
To some degree, it can be done. The experiment actually is done in helium atmosphere, because the soft X-ray gets absorbed if you do it in air. So there's a certain degree, and in fact, people attempting to do it. It's doable. In fact, there's some experiment they are done. And the great way about STIXM is that you can actually look at the behavior of an individual nanostructure, not collectively.
Okay, thank you. And a new question for the audience. Okay, just Chinese I translate. Can we directly distinguish the amorphous structure and the crystalline structure by XAS test at the atomic level? For example, silicon you can mention using the slide. Yeah.
Sorry, can you repeat the question?
Okay, can we directly distinguish the amorphous structure and the crystalline structure by XAS?
Yes.
X-ray, yeah. At the atomic level, yeah.
Yes, but the spectroscopy, yes, but spatially, no. If that's what the question is asking.
Okay, thank you.
Because synchrotron, the state-of-the-art synchrotron now can be focused to a couple of nanometers, but I think it's difficult to reach to Armstrong resolution. So, and if yes, we're very high resolution, we can distinguish the chemical state of silicon even in a mixture.
Okay, thank you. I think the coordination number are different for amorphous structure and crystalline structure, yeah. And
yes, those can be done just by XF, which I did not talk about.
Okay.
Because XF allow you to determine the interatomic distance and the number of labeling atoms. And if the data is good, it can also determine how they are vibrating.
Okay, thank you. And another new question for the audience is, in the beginning you mentioned the heterojunction structure, and how to make clear the atomic structure in the interface. as compared to counterparts, components or heterostructure.
Those heterostructure in principle can be studied with TEM. What X-ray can do, what we are doing here is to understand energy transfer, electron transfer, or mass transfer across the interface. And we look at the interface from a spectroscopy perspective, not from a spatial perspective. And to do that, I think TEM is better.
Okay, thank you. I think most audiences are interested in your group, your work. So they just wonder, what's the recruitment of PhD students and postdoctors or visiting scholars in your group now? Thank you.
Can you repeat the question, sorry?
I think some audience just wonder the recruitment of PhD students and postdoctors in your group. So they just wonder. Just ask.
We have many people here in our center doing this kind of work. And yes, the answer to that is yes. They could just come to our website and take a look.
Okay, thank you. Thanks, Professor Sham, and thanks for your response to all questions, and thanks again for your time. And also, welcome to submit your work to SmartMed. And good night. Okay, bye. And now, let's welcome the next speaker, Professor Zhifeng Ding. First, please allow me to briefly introduce Professor Zhifeng Ding. Dr. Zhifeng Ding is a full professor of chemistry at the University of Western Ontario, London, Ontario Province, Canada. He received his bachelor degree in chemistry with the highest honor at the Southeast University, master degree in coordination chemistry under the supervision of Professor Xiaozhen Yu at Nanjing University, and earned his PhD in physical and analytical electrochemistry in the Girard Group at the Swiss Federal Institute of Technology in Lausanne. After 3 years postdoctoral research in Allen G. Bard Lab at the University of Texas at Austin, he moved to his present Canadian University as faculty member. His research focuses on scanning electrochemical microscopy, ionic liquids as lower electronics, electrochemiluminescence, and solar cells. Recently, this group has utilized graphene cotton dots for LED applications. He has published more than 170 papers, filed more than 4 US and Chinese patents, which has been cited more than 7,320 times. Oh, sorry, let's share the screen. For screen. Okay, thank you. Dr. Ding has received several awards, including most recent Science Distinguished Research Professor, Western University Faculty Scholar, 2017 Canadian Society for Chemistry for his significant achievement in chemistry, 2017 and 2018 Western Vanguard Awards for finding patents in solar energy, 2018 Ecl Award for electrochemistry and electrostasis for his contributions to solar cell research, honorable speaker for the Brinka 2016 Nobel Laureate winner, advanced chemistry lecture series at the East Channel of Science and Technology in 2018. Okay, today Professor Ding will give a talk about smart materials for electrochemiluminescence and photoluminescence. Let's welcome Professor Ding, please. Thank you. Hello, Professor Ding. Now you can share screen.
Yes.
Okay, please.
Yeah.
Thank you.
Can you see?
No full screen now. Yeah.
First, I would like thank the organizer.
Sorry. Now not full screen. Okay. Thank you. Okay.
Yeah. First, I would like to thank the organization committee to invite me to give this talk. And I have been at Tianjin University several times and give a couple of talks. So I have really good impression of Tianjin University. And in my talk, I will go over a little bit my research related with the research at Tianjin University. And also, I would like to thank Professor Zhang's kind introduction. So today, I'm going to talk about these smart materials for electrochemiluminescence and photoluminescence. Okay, so this is kind of my traveling. Okay, so from Southeast University to Nanjing University, okay, they are in the same city, Nanjing. And then I learned French at Beijing Foreign Studies University and University of Fribourg in Switzerland. And then I went to EPFL, that means Swiss Federal Institute of Technology, to study my PhD. And then I did a postdoc, and then I moved finally to Canada, University of Western Ontario, in abbreviation, Western. And this is kind of the map of Canada, and we are really in the south here, UWO, University of Western Ontario, and it's kind of inside the United States, okay, inside Michigan State. And if we zoom in, and we can see London, Ontario. And this London is exactly the same spelling as British London, but of course, much smaller city. We have 400,000 people. But in Canada, it's already the number 10th largest city, population-wise. And London is very convenient. Okay? You can go to Toronto in 2 hours, and you can also go to Detroit, 2 hours, and you can also go to Buffalo or Niagara Falls, also around 2 hours. Another thing is that we are inside the 5 lakes, and these lakes' name is called Huron, Ontario, Michigan, Erie, and Superior. And Canadian people like put the first letter together, called Lakes Homes. And we are very close to the Niagara Falls, and you have this 150-meter chute, okay, this kind of fall. It's very nice, and this is Canadian side, and there it's US side. So, okay, I'm running a lab of electrochemistry, spectroscopy, and microscopy for biology and energy. Okay, basically, it's kind of materials. And we have like 4 sections. Okay, so that means we have the photo electrochemistry, the scanning power microscopy, mostly is the scanning electrochemical microscopy. And then we have the electrochemistry at the microinterface for the ionic liquids as a new electrolyte. All right. And I just go a little bit about the recent scanning electrochemical work, but this is not my focus. So recently we published on these journals. Get this, and then get some front cover or inside covers. And then we talk about this photo electrochemistry, and in fact, we are making solar cells, but it's a thin film solar cell. Basically, it's copper, zinc, tin, and sulfur semiconductor alloy, and this is kind of black for light absorbing. And then we get kind of other layer for deposition to finish. For example, the cadmium sulfide, this yellow layer, and then we do the atomic layer deposition for the zinc oxide. And then we just get this kind of contact, electric contact, and then we get this solar cell. And these are the 2 students, now Dr. Turnbull Matthew did this, and then Vichy is graduating master students. So you can see here, okay, we just get like really kind of tiny photo electricity conversion here, 0.49% and to 7.7%, and then recently we get 8.5%. So that's the thing we're doing. And Dr. Sham just gave a talk in the last hour about the synchrotron. And we collaborate very well with Dr. Sham using the advanced photon source. This is in Chicago. And Canadian light source has one beam line. It's a sector 20 beam. It's a CS, Canadian light source. And we went there to use it because it's quite close. And with that, we can see that we have Matthew Turnbull graduated, defended his PhD thesis with this work, all along with kind of a synchrotron to characterize layer by layer of our solar cells. All right. So, but this is not my topic today. So, I'm going to emphasize, or I'm going to focus on the electrochemiluminescence, or we can also call it electrogenerated chemiluminescence. And in China, it's really popular. I can tell that there are thousands of researchers doing this electrochemiluminescence for various purposes, like applications in bio detection and other kind of applications. And many Chinese scientists are really famous. For them, some people at Nanjing University, I will not mention the names, but many. And at Southwest University and many other universities. It's almost every, and even we should mention that Changchun Institute of Applied Chemistry, we have several groups doing this electrochemiluminescence. But still, I would like go over a little bit the principle of this electrochemiluminescence in annulation mechanism. And you can see here, this is a molecule called 9,10-diphenyl anthracene. So 3 benzene together is anthracene. And then 9,10 position, we have another 2 phenyl group, the benzene groups. And then we have this 5 benzene rings. It's called DPA, diphenyl anthracene. And then we just immerse 1 electrode to this diphenyl anthracene solution. And we just apply negative potential. So then the electrode is rich in electron. And then it will inject to the lumen of the DPA. So we get it called DPA radical anion. And if we switch the applied potential on the electrode to positive, like here, then in the vicinity of the electrode, now the electrode is poor in electron. And then it will take the electron from the DPA, diphenyl anthracene, this HOMO, out, and then get into gain the electron. So then the DPA will become DPA radical cation. And then you can see here, the 2 radicals, we just get 1 electron exchange. In fact, electron exchange from their HOMOs. And then you can see here that if this electron moves to there, then you get just 1 ground state. And then this guy becomes the excited state. So it's kind of a rate phase. And then the excited state of DPA just goes down to the ground state. The electron on the lumen to the HOMO, and then goes down to the ground state and emits light. And that's the whole process is called electrochemiluminescence. And what's and we can also so in the above slide we talk about this annihilation mechanism. That means it's the electron transfer between radical cation and radical anion for the same luminal form. But we can also do this called electrochemiluminescence of co-reactant system. And in fact, so like Lupipi, I use this Lupipi as an example. Okay, so you can just oxidize the Lupipi or reduce the Lupipi. So this is oxidized Lupipi, and then you can also do this kind of oxidation of the oxalate, and then the two guys here just get electron transfer, and then we get the Lupipi excited. And other co-reactant like tripropylamine or persulfate or benzoyl peroxide, it's kind of similar. If you are interested, you can read our publications. So at Western, we just developed this kind of Esil instrumentation, and we from 2003 we officially just begin the Esil study. And I would like to show two examples, small movies. So this one, the first one, is just a DPA. And if I click the play button, and you can see the light is kind of purple, right? A little bit of noise. I'm sorry. And this one is, in fact, it's a Lupipi solution. If I click on the play, and you will see the orange color. Okay, I just go back and then to play this movie. You see. So that means with our naked eyes, we can see this kind of electrochemiluminescence. And what's the application? In fact, Roche, the pharmaceutical company, headquarters is in the Europe, and they just do this. Okay, so in fact, they use electrochemiluminescence as an immunoassay. So basically, we just label the antibody with the Lupipi. That's a typical one. And then we get the other antibody unlabeled to connect to the magnetic particles. And then you get this electrode and you just apply the magnetic field. And then you just fix these kind of magnetic particles with the antibody. And then you just throw in the antigen, this guy. And then you just, again, throw in this Lupipi labeled antibody. And in this case, we can tell that if it gives the Esil, electrochemiluminescence, then this is a 1-to-1 ratio to this antibody, and a 1-to-1 ratio to this antigen. In this way, we can measure the antigen. And recently, Professor Miao in the United States, he published in scientific report that we can also detect the virus, but it's not the COVID-19 yet. But if we can find the antibody of the COVID-19, then we can also do this kind of principle. So basically, we just get the antibody labeled, and then inside it's not the antigen, but it's the whole virus. This is also possible. Another application, in fact, we are doing here at Western, in fact, it's called light-emitting electrochemical cell. And we would like to use graphene quantum dots, okay? And we just get, in fact, we get this kind of tinned copper, on the PCB, and then we just use the P-dot PSS conducting polymer to flatten the surface, and we get GQD, the graphene quantum dots, and then we get aluminum doped zinc oxide. In this way, it's done. So in fact, in theory, it's just one ITO and one aluminum, and then one of your light emitting layer. I'm going to show you this simplest technique we are developing. So in fact, this layer is ITO, this is glass, and then we get this is graphene or carbon quantum dots here, and then vertically we just get this aluminum electrode deposited, and then we can get this kind of many devices. It's called device array here, and in fact, this kind of devices are making by Kenneth, John in my group now still, and Professor Ray Zhong Zhang at Tianjin University now. She worked here almost 3 years, and she knows how to make these things. And this is a photo she just used. Okay, so in fact, in our lab, we make all these kind of spectrum of the light with different kind of luminophore. Okay, so in fact, you can see here, we can get this kind of bottom up. That means we just prepare the graphene quantum dots from the chemical precursors, and then we'll get this kind of light emission. And we can also use the PDY 132. In fact, it's called super yellow. It's a polymer, and we can get this kind of yellow. And we can also do the top down. That means I'm going to talk about this. In fact, we use the graphite and do the electrochemical exfoliation, and then get the graphene quantum dots. And this will be in orange. And you can also get this LUPP is in orange-red side. And we also have the collaborator at the University of Calgary in Canada, Professor Welsh. He surprised with this kind of single molecule graphene quantum model called PDI, and we can get even this kind of near infrared. So with this kind of different materials, we can make this kind of light emitting electrochemical cell here. So now we just return to here, Electrochemiluminescence, and we would like to begin with this called gold clusters. Gold clusters. And in fact, we do our instrumentation at Western ourselves. So basically, we just have this electrochemical cell normally, and we just repress the bottom as a transparent window, and then we use a photomultiple tube to detect the light emission in the vicinity of the working electrode. And then we feed the light intensity to the computer. And simultaneously, the potential stat also feeds the potential and the current to the computer as well. So then in this graph, you can plot the current, the electrochemical current, as here. And we can, versus the voltage, and we can also, this is called a cyclophotomogram. We can also plot the Ecl intensity versus the applied voltage. We call the Ecl voltage curve, which is red. And this is kind of a zoomed in picture of this kind of a computer screen. And we can see that this light emission, the Ecl emission, is very low. It's not very discoverable. So then we can use this tripropylamine. I showed in the previous slide the oxidate, but we can also use the tripropylamine. So this is the structure. And we just oxidize the tripropylamine, and then this depolarize once. And then we get this called the tripropylamine radical. And this has really reducing potential very high. It's negative 1.7 EV. So basically, it can reduce everything. So that's kind of the electrochemistry for this tripropylamine, and you can see no light emission, just tripropylamine. This is kind of let's say background check. And then we see in the last previous slide that we don't have much the Isil intensity for this gold cluster 38, and this is called 38 gold there, the yellow color, and this red, the sulfur, and then the other kind of coupling ligand. And so now we just add this TPI as a co-reactant, and then we can see here, say, okay, now we see some like a photochrome. In fact, we use the same device and same instrumentation, and it's easy. So now we can see here, we say the TPI has really high reducing potential. That means you have the electron, you can inject into the gold 38, okay? And then we can see here, we get this gold 38 excited state, okay? And we can get gold 38 plus star and gold 38 3 plus star, okay? So this is color coded. But the thing is that if we look at the spectrum, and then we can say, okay, the photoluminescence and the Isil spectrum, they are almost the same. That means even different excited states, they get the same spectrum. Then we say, okay, this is not smart material because we give the stimuli at a different potential, and then we get the same response. Okay. How can we solve this point to get smarter gold clusters? And here we are. We just worked, in fact, the gold 25 cluster negative, and gold 25 zero charged, and gold 25 plus charged. And we already showed you the gold 38. And we also worked on gold 144. Okay, so these crystal structures are not from us, from the literature. I will tell you later who did that. And from these gold clusters, we would get smarter gold cluster. That means we give the external stimuli, and then they will respond differently. So that was our goal. And before I went through, I would like to point out the pioneers on gold clusters. Professor Royce Murray at the University of North Carolina, champion here, and Professor Longcao Jing at Carnegie Mellon University, and Professor Manzhou Zhu at Anhui University, Hefei. So these are the pioneers to make gold cluster. But my postdoc, I will show you, Dr. Marty Hasuri, he can make really well gold cluster. But of course, in reference to the gold clusters these guys are making. And the crystal structure I showed you in the previous slides mostly are determined by these guys. So now I would show you, say, okay, continue on this smarter gold cluster, and I would see the EChem, the electrochemistry. So you can see here, the gold 25 zero is here, and then it's here. And then you can oxidize it to gold 25 plus. And you can also do, gold zero is here. And then you can also do this gold 25 2 plus. You can also reduce the gold 25 zero to gold 25 minus. So we can link these redox potentials by this. So we link it together. And then we measure the photoluminescence, and to get these peak wavelengths and convert it to the electron volts. And in this way, we can link different gold cluster and their excited states. For example, gold 25 negative charged, then it's the red one. Right? And with the peak wavelength 950 nanometer. And gold 25 0, this is the green one, with 850 nanometer peak wavelength. But the emission, they are kind of moderate. But if we use gold 25 plus, you can see we have 860 nanometer, this is the blue one, but much higher, okay, more than twice higher. So in this way, we can distinguish via the light intensity and also the wavelength, then these three species. So now we took these three values and then we just get together. So then gold 25 negative can be excited to gold 25 negative excited state, it's 1.31 eV. And similarly, gold 0 to gold 0 excited states, gold plus to gold plus excited states. And as I said, this is done by Dr. Mahdi Hasri, who was a PhD student in my group and in my colleague Dr. Walkenden's group. He's a joint PhD student. And in Walkenden's group, he was making the compound, and in my group, he's measuring the electrochemistry and photoluminescence. So now we just reminder from the EChem electrochemistry, we see these links, and from the photochemistry, we see these links, and then from thermodynamics, we can calculate how do we transfer from the gold 25 negative excited state to gold 25 2 minus. What's the energy? And this we call the Latimer type diagram. Okay? So with that, we can see here, even we put the different molecular orbitals, HOMO and LUMO. We like these HOMO LUMO. In this way, we are very clear, if what we are talking about, the gold 25 negative, gold 25 2 negative, gold 25 0, gold 25 plus, gold 25 2 plus. And then we have three excited states. Get that? So we can, through this diagram, we can get everything we understand. And then we would say, okay, can we get smarter materials through this diagram? And the answer is yes. Let's see. Okay, so as I said, we are also developing the analytical instrumentation. So in fact, one technique we developed is spooling Ecl Spectroscopy. And in fact, it's not that fancy, difficult. So we use the same Ecl cell, and then instead of just detected by the PMT, photometric tube, we just use a spectrograph attached with a CCD camera. So the spectrograph just split the spectrum at different wavelengths, and then the CCD camera just take a picture. In this way, we do this. We scan the potential, and then we should see the Esil evolution and devolution through the spectrum like this. Right? And then we would see if it's if this gold 25 cluster is smart material or not smart material. So to show you the principle, as I said, here we just scan the potential, or you can say, oh, it's a time. And then here and here, this is light intensity, and this is the wavelength. So this is 3D picture we call the spooling Ecl spectroscopy, and I can show you. At the beginning, it's nothing, and then you get Ecl evolution, and then you get Ecl devolution. So if I click on display, and you can see it just goes to the back, and then take picture. So almost every 1 second, we can take a picture. And then we can get this kind of called spooling Ecl spectra. So that's the principle. Okay. So now with this, okay, we will show you how smart the gold 25 cluster. So okay, we just use gold 25 0, okay, 0 charge. And then we just begin to apply, okay, scan the applied voltage, in fact, 0 excite states. And we showed you the photoluminescence spectra. In fact, it's the same as the Isil spectra. This should be 880 nanometer. Although it's not very, it's a little bit noisy, not very clear, but the peak wavelength is 880 nanometers. And then we just continue the scanning. So that means when you apply the higher voltage, then you can continue to oxidize the gold 25 plus to gold 25 2 plus. And the same thing, TPI still get oxidized to the TPI radical cation, and then deposit ones get TPI radical. And then this gold 25 2 plus react with TPI radical, and then give you gold 25 plus excite state. And this should be given the peak wavelength at 880 nanometers. So these two voltages just tell us by changing the applied voltage, we can tune the emitting species. That means 860, 880 nanometers, so different excite states. So now we can define this gold 25 is kind of smarter material. And with different stimuli, then we can get the different response. Even more, we can also change the TPI radical, TPI concentration to 200 millimole. And you can see here, so because this is kind of a strong reducing agent, it will reduce everything. That means reduce the gold 25 0 in the solution and to gold 25 2 minus. Okay, and then this gold 25 2 minus react with TPI radical cation, then it will give you gold 25 minus excite state, which is at 960 nanometers. So on this slide, this gold 25 is also kind of a smarter material and will respond to the stimulus of the radical concentration of TPI. Okay. So I just show you this kind of example, and then I will show you the silicon nanocrystal quantum dots. And this work I was doing with Professor Alan Bard at the University of Texas, Austin. So in fact, we have this silicon quantum dots made by Professor Coggle in their chemical engineering department. And he just gave us this, and you can see that so different silicon nanocrystal size can give you different colors. And in fact, he gave us this blue color. Then we do the electrochemiluminescence with the silicon nanocrystal. And in fact, you can see that the wavelength is way redshifted. Okay? So then we develop this kind of schematic. So that means if you excite these silicon nanocrystal with the light, that means you generate the photoluminescence, then it's blue. But if you excite these nanocrystals with electricity, then you get this kind of red light emission. So we still can define that silicon nanocrystal quantum dots, they are smart. That means different stimuli, you can get different response. And we can control with this. Okay? So it depends which color you would like to get. If you would like to get blue, then photoinduced. If you would like to get this kind of a red, then do the electrochemiluminescence. Okay. So the other example, I would also show you the graphene quantum dots. And in collaboration with Professor Andy Sung, he will give a talk in 2 days. And Professor Sham, he just gave a talk. Okay? We just can do the electrochemical exploration of multiple carbon nanotubes. Okay? We apply the electrochem, and then it just get these kind of graphene quantum dots. That was done in 2007 by one of my first PhD students, was Dr. T.K. Sham, now Dr. Zhou at the CLS. So that's kind of the previous work. And then this time, we just use graphite electrode, and then we do the same thing. And fortunately we get the same graphene quantum dots, but with much lower cost, because multiple carbon nanotubes we still need to prepare, and it's expensive, while this graphite is much cheaper. So we just get these this graphene quantum dots by what we call top-down method. That means we do the electrochemical exfoliation. And then we can see here we have this excitation spectrum, and we have also this emission spectrum. And you see, it also gives you the blue emission at 445 nanometers. And then, so this work was done by Kenneth, Jonathan, this John, and Sui Jin, now is Professor He at Nanjing Forestry University. And also another PhD student, Liu Qingyang, and then another master student graduating, Jonathan, so he's going to graduate by this December. So we do the electrochemiluminescence of these graphene quantum dots, and in fact it's nitrogen doped, and we can get these kind of spooling spectrum. Nice. It's strong. However, we did notice that these graphene quantum dots give you the Isil is around 600 something. And I emphasize that with the photoluminescence, it's blue. So similar to the silicon quantum dots, we can just give the different stimuli, then we can get different responses from these smarter materials. More, as we said, we just prepare these graphene quantum dots and then get the light emitting electrochemical cell as this. Like basically, it's 3 layers, and I already showed you the structure. So, and fortunately, we get the light emission from this kind of device, and that was really exciting. And this, and in fact, this from the CIE color diagram, it gives you the white. And Chemistry Olympic Journal, they like our kind of research, ask us to give a kind of inside color. Okay, so now I would like show kind of my last example in this talk. So in fact, I'm going to show you just simple molecules. It's called Diborum Complex. So you see here, we have this boron, and we just connect them together. And this was synthesized by Professor Hongbo Wang at Zhanghan University in Wuhan. And Professor Wang is our alumni at Western. He graduated from our chemistry department. And in collaboration with another Professor Wang at Xi'an Jiao Tong Liverpool University and Professor Bing Yang at Jilin University, and we did the work, and finally we published it in Annual 1. And these are the major contributor. Jonathan, graduating master student, and Professor Zhang Nao at Tianjin University, and Liu Qing Yang, the PhD student. So I just would like to tell you something really kind of exciting. So in fact, this diboron compound, Professor Hongbo Wang, he got the crystal structure. And you can see that in a single crystal cell, it packed two. So it's kind of packed. And this possibly will cause the called restriction of intramolecular rotation, RIR. And in fact, it is. So you can see that these two photoluminescence spectra. So this blue one is called crystalline film. So Jonathan and Professor Zhang and Liu Qing, so they just made the film and then shine with the light. And then eventually we get this blue shifted photoluminescence. And if they dissolve the compound in a solution, like acetonitrile, and then they observe kind of red shift. And the blue shift from this red is kind of 67 nanometers. And you possibly say, you possibly kind of wondering what's going on. And I already mentioned that there's RIR, restriction of intramolecular rotation. So we just follow that kind of thought. Say, okay, so if we just get the powder and then we shine with the UV light, you can see it's kind of yellow. You see, grounding, it's kind of yellow. And from yellow to ground. So with mechanical grounding, you can see from the crystal is yellow, and then you go to kind of orange. It's red shifted. Or from the powder to crystal, it's blue shifted, like 67 nanometers. Okay, and eventually, if we give a stimulus of acetone vapor, then you can see this powder, which was kind of orange color emission, gives you back to this kind of a yellow, blue shifted. And this we call crystallization induced blue shift emission. It's very interesting. And we also did this X-ray diffraction spectra, and you can see that the crystallized one, you can see very sharp kind of crystalline peaks. However, when you mechanical grounding, then you see this kind of a broad. Okay, so this is called Cie emission, or called CIBSE. Okay, so in fact, this is related with Tianjin University. Okay, I know you have the ARE Research Institute, and the director is Professor Li, okay? And the honor director is Professor Ben Zhongtang, who invented this called ARE, and of course CRE as well. I'm going to explain to you what's going on. So in fact, if there's some restriction, that means by this kind of a packing of the crystal, and then you will get the packing, and then you enhance this kind of homo-lumo gap, and then you get blue shifting. And this was proved by DFT calculation. And this one, in fact, if you just get a solution, you don't have the RIR, so then you get kind of red shifted. Right? So that's the thing. Then how about the Esil? So in fact, Esil we get similar thing. So if we just have the film and put in the solution, we have this blue shift because we still have this RIR. However, if we just put this one and then with the co-reactant kind of film solution interface, and then we get this kind of red shifted. So in this way, we find that CRE plays very important role, and it could enhance the Esil light intensity like 20 times. And that's kind of the work. So I think I control well my time. I'm going to wrap up my talk. So you can see here, with these smart materials, we have great opportunities for many applications. Today, I only show you the electrochemiluminescence and photoluminescence application. We can also get the grand avenue towards this smart material application of electrochemiluminescence and electroluminescence. That means we get this kind of light emitting electrochemical cell. And I would like also say that the journal launch of this smart material is very timely. And I would like congratulate the launch of this journal. And I would like acknowledge these units, our electronic shop during the instrumentation, and also the support from the university and the funding agencies. Of course, don't forget all the students. And I would like show you several photos of our campus with our people in the group. And you can see here so many photos. And here is Professor Zhang and Professor He, and still these two are already become doctor. And then I have here PhD candidate, and master candidate. And I would thank you for listening. And I just show you this picture I always show. This is French. C'est le soleil revient toujours. That means the sun always comes. So that means with the solar cells, with the light emitting diodes, with the smart materials, we always can get the rich light. Thank you again.
Hi, Professor Ding, and thanks for your wonderful talk, and thanks for your praise to SmartMath. Yeah, thank you. Now I will host the Q&A session. Our staff have collected some questions from the live platforms for you to answer. I just checked it, so many questions. Sure. They are interested in your talk. Yeah, thank you.
Okay.
And I will ask the question on behalf of the audience. Yeah. So the first question is, I think he or she mentioned, I have read a lot of your works. I'm wondering the minimal size of actual microelectrodes in your lab. Can it reach nanometer level?
Okay, that's very good. Yes, the answer is yes. Okay, we did make a kind of a nano electrode as small as 50 nanometers. However, this is about scanning electrochemical microscopy. However, the stability is not that good yet. Okay, we are still working on that. Thank you.
Okay, thank you. another new question from the audience. For your LEEC device fabrication, can you adjust the emitting colors? How many colors can you get now? And how to evaluate these devices? Thank you.
Yeah, this is a really good question. So in fact, our purpose is to get white light. All right. So it's white light. And for the Esil, as I showed in the spectrum, we can get all the colors with different materials. But that was our original thought. Say, we can mix the three colors. That means this red, green, blue, and then we can get the white. And eventually, we were really excited to know that with graphene quantum dots, in fact, because originally the PL is blue, however, the Esil is kind of red or yellow, and then the EL, that electroluminescence, in fact, is white, and we were really happy.
Okay, thanks for your response. And another question is, he or she mentioned, the audience, you did many quite good works on Esil. Yeah, you mentioned, especially one paper published in Science. For different Esil emitters, you have showed organic compounds, inorganic complexes, and nanomaterials. Do you think which class is best and most promising for real applications? Yeah, thank you.
Very good question. Very good question. In fact, I would say for the organic molecules, in fact, these boron and diboron compounds, especially the body P, they are really strong emitters. So this one. And for the inorganic complexes, LuPP and iridium complexes are really good. And for the nanomaterials, for Esil, gold clusters, in fact, are kind of best, but it's only in the near infrared. But graphene quantum dots, it's not bad at all. So we are still working hard to enhance the graphene quantum dots emission. In fact, we are not really the top expert for this graphene quantum dots emission. And in fact, in China, Professor Lou at the Beijing Normal University, her group is really good. Get really high graphene quantum dot emission, and we try to work hard get high emission graphene quantum dots at a low cost.
Okay, thanks for your response. And another new question for the audience. These days, he mentioned or she mentioned, a lot of works have reported double or even triple metal nanoclusters. What about the Esil of these multiple metal nanoclusters relative to single metal nanoclusters? Yeah, thank you.
Yes. I hope this is not from Professor Manzhu's group, okay? Because as I know, Professor Zhu, I only mentioned the gold cluster expert, but Professor Zhu at Anhui University, he's also the expert of this kind of we call mixed metal clusters. That, for example, gold, silver, gold, palladium, and others. Actually, we are trying some like silver, and the results. Okay, I can tell you. Okay, I got because we are not good for the synthesis. I got a sample from South Korea. Okay, Dongqing Li, Professor Dongqing Li. So in fact, the emissions are not very strong. Okay, from Dongqing Li's sample, but their purpose is not for Esil, but for catalysis. So I think for catalysis maybe it's good, but for the Esil emission is not really good. But ourselves, my postdoc, Dr. Hassuri, he can do some synthesis. Yeah. So he exchanged gold cluster to some like a mercury gold cluster, And in fact, we did observe from this mercury gold cluster, this kind of mix, but it's quite strong. But I still think we need to think about the gold cluster structure. I still think gold cluster should be good. So we need to think about this gold cluster electronic structure or bonding structure. And recently, Professor Zhu published a very good paper about different crystal structure of the same gold, like 20, I think it's 21, gold 21 cluster, but with different kind of crystal structure. And they just say, okay, the reactivity is different. And this reminds me that possibly the Isil reactivity is also different. So we are working hard toward this kind of direction.
Okay, thank you. And another two questions from the audience. I just combine together. What's the role of what's the role of Isil in the development of smart materials? And you mentioned it finally, in your slides. And how to apply it in solar cells? Yeah, thank you.
Okay, yeah. This is different kind of nanomaterials. So as I mentioned in my beginning slides, in fact, we use copper, zinc, tin, sulfur, semiconductor alloy. And the problem is that the preparation of nanocrystals, it's kind of problematic because we cannot get kind of homogeneous. However, what we found that from our electrochemistry, in fact, it's really good. So we did electrochemical deposition, right, for different layers of these, for example, copper, zinc, tin, three layer. And then we just do the annealing and sulfurization or selenization in a furnace tube. And these ones are the best quality kind of Isil. Not Isil, so solar cell kind of light absorbing layer. Okay, remember, Isil, for the light emitting device, we should get emitting layer. But for the solar cell, we should get absorbing layer, light absorbing layer. So it's kind of different purpose. But anyway, it's a photo electrochemistry. It's different way. So one is give the photon and get the electricity, that's solar cell. And the other one is that apply the electricity, you get the photon, that's Isil, or light emitting devices. That's very good question.
Okay, and thanks, Professor Ding. Yeah, still so many questions. I think it's too late. Yeah,
you can go ahead.
Maybe close to
no point. No, it's good.
So
we can do at.
Yes, if you have more questions.
We can do until 11. No point.
Okay, maybe we can send an email to Professor Ding. Yeah, I think the Professor will reply in details.
Sure.
Yeah. And thanks for your response to all questions. Yeah, and thank you for your time. And also, welcome to submit your paper to SmartMed. Yeah, thank you. Yeah.
Sure,
okay, good
I
night.
will.
Thank you.
Good night.
Good night. Okay, bye.
Bye.